Hi everyone, my name is Wei. Today I'm going to present our work SympleGraph. Graph is a very important algorithm in social networks, bioinformatics, and many other real-world applications. There are two types of graph processing systems. One is shared memory systems that has no scalability but very high efficiency. While distributed system has high scalability, they have low efficiency. This is mainly due to the distributed overhead in system and programming. Previous work have studied this topic for a very long time. In this paper, we will propose a common problem in today's programming abstraction. To begin with, we will first review the popular vertex-centric programming abstraction for graph. The key idea is to apply a user-defined function h for each vertex. The function h takes the neighbors of this vertex as input and outputs the new value of this vertex. We can see an example of vertex-centric programming for bottom-up BFS. In this function, it traverses the neighbors of vertex v, and if the neighbor u is not visited, if vertex v is not visited and vertex u is in the frontier, we will mark u as the parent of v and mark v as visited and in the frontier in the next iteration. It is important to note that we have a break statement at line 9. It means that we can skip the traversal of other neighbors if we have found the one neighbor that satisfies the condition. Now we come to the distributed context, when the graph is large enough so that the neighbors of a vertex cannot fit in one machine. On each, there are 4 neighbors, and each machine has only part of the neighbors. So people have invented the concept of master and mirror vertices. There is only one master vertex of V, and the mirror vertices are its replicas on each machine. So the updated values will be first generated on the mirrors. And people use 2 functions instead of 1 function to define the graph algorithm. So the first is a function I that gathers the update and sends the update to the master vertex. The second function is C that combines all the updates from different machines. We can see an example of distributed bottom-up BFS here. So here we have 2 functions. It's very similar to the function we have seen in Edge, except that it is broken into 2 parts. And in function I, we have a emit function that will transmit the update from the mirrors to the master. In this distributed programming, the function h, I, and c have to follow the following properties. So the first one is h is decomposed into I and c. This is to make sure that the output is correct after you transform h into 2 functions. The second and third property is that C must be associative and commutative. This is so that we can combine the messages in any order. But the most important property is that I should be homomorphism. It means that we can process the neighbors of V, U1 and U2 independently in parallel. So this is to ensure efficiency and parallelism. And these 4 properties are common in previous programming abstractions. However, we find that for some graph algorithms, I might not be a homomorphism. When I has a dependency, it means that the processing of U2, if we know U1, can be different from processing them independently. One simple example we have seen in the bottom-up BFS is that if there is a break control flow in function I, then we can skip the computation of the following neighbors, and we can also skip the update messages sent from the mirror replica to the master. So this is the motivation. If I is not a homomorphism, there we are actually doing redundant computation and communication in current systems because we are defining a very strict programming abstraction. So far, we have introduced a formalization of distributed graph programming languages, and our motivation is that if there is some dependency in the graph algorithm, it can potentially reduce computation and communication. So we propose a simple graph to solve this problem. The high-level idea of simple graph is that we add a new type of communication in the system, that is the dependency system. Instead of only sending the update message to the master independently in parallel, we do a dependency communication from mirror to another mirror and make sure that there is that the processing of neighbors is follows a sequential order. So the key idea is the dependency communication. And simple graph has two parts. The first is the compiler, and the second is the system. The compiler part, we define the dependency data type and dependency communication primitives, then which instrument function I. We can see an example here. This is a new version of bottom-up BFS using the dependency communication. First, we define the data type of our dependency communication. For BFS, we only need 1 bit of message to indicate whether we can skip or not. In the function I, before we enter the function, we will wait and receive the dependency from previous mirrors and check if we can skip the computation. The other parts are the same, except that when we are sending the update message at line 9, we also need to send the dependency message at line 10. So above this, the compiler part, but we have some serious challenge in the system because in previous systems, for efficiency, I should be parallel, but in order to enforce dependency, I should be sequential. The solution is that we can use scheduling to, so we can schedule I of different vertices to be parallel, and for each vertex, it is sequential. So this is a well-known technique called circular scheduling. So we will divide an iteration of computation into several sub-steps. The number of sub-steps is equal to the number of machines in the system, P. And we have a sigma, it's a circulant permutation. In each step, J, we will run part of the neighbors on a specific node based on the circulant permutation. We can see a simple example here. Suppose we have 2 machines that we are doing things in parallel. And the 2 machines will start from different parts of their neighbors. So in the first step, they will start from 2 different neighbors. So the processing of them can be done in parallel. And after processing these neighbors, they will send the dependency message. In the next step, since we have already sent the dependency message, we can start executing on the next machine. And the following is also similar. So in this way, we are actually scheduling the processing of different vertices to be parallel, but if you just look at one vertex, the processing of its neighbors is sequential. Based on the circulant scheduling, we can design a simple graph system. We also do other system optimizations. For example, we differentiate the dependency communication for high degree and low degree vertices. So the purpose of SympleGraph is to introduce dependency communication to reduce update communication. However, for low-degree vertices, because it has a small number of mirrors and the update communication originally is low, so it is not too beneficial to introduce dependency communication for low-degree vertices. We can see an example here. The low-degree vertices only has one mirror and one update message. It is not necessary to transmit the dependency messages across all the machines. However, for high-degree vertices, it has neighbors on all other machines. And if we can transmit the dependency message, it is very likely that we can save more update communication. We also have other system optimizations like double buffering, RDMA, and numeral wheel. Please see more details in our paper. So the last part is evaluation. We compare our system to two state-of-the-art distributed graph processing frameworks, Gemini and Glue, and we tested 5 algorithms that has the property when I is not a homomorphism. These are very basic algorithms and widely used, like BFS, K-core, K-means. We also tested many graphs and very large graphs. So first, we can see that our system SympleGraph outperforms state-of-the-art by 42% in almost all graphs. And we can explain that the source of Speedup is the computation and communication reduction. SympleGraph traverses less number of edges in the graph than previous work. It reduces computation by 67%. SympleGraph also reduces communication. So although we add a new type of communication called dependency communication, since we can reduce the number of updated communication messages significantly, the total communication is also reduced. On average, it is reduced by 41%. In conclusion, in this work, we have a formalization of distributed graph programming languages. So we review all of the previous frameworks and identifies that the loop carry dependency problem exists. This will lead to redundant computation and communication. We designed a system, SympleGraph, that enforces the dependency, and the system is efficient due to its scheduling. If you are interested, please come to our talk. Thank you.